Dear colleagues, it is my pleasure to open a conference, Fractional Calculus and Time Frequency Analysis, which we organize, Professor Daniela Reiter, Professor Teofanov, and Professor Biljana Nedeljko, our secretary. And from the early beginning, we didn't plan a conference in that form. Actually, we have very good connections with our colleagues from outside, especially with the group in Vienna, led by Professor Balas and Feichtinger, as well as a group of Professor Kiryakova from Bulgarian Academy of Science, and conference was somehow planned in that way, that we will just have a working conference, and then happened what was happened. Nobody expected how it will go on. Our colleague Arpa Takaci passed away in the meantime, and this was a really shock for us, for his family especially. And so somehow we decided to make this conference in this form. So we have a part here in Novi Sad. You can see public in Novi Sad, and probably a good audience out of our country on the platform, WebEx platform. I think in the end we have more than 20 participants from outside. From more than 10 countries, and so it's a rather big conference, and we somehow do not have so many lectures from our group in Novi Sad because it will last more than 2 days. And so this is how we organize this conference, and it is first one organized in this way, and we believe successful one. Especially I would like to welcome our Dean of Faculty of Sciences, Professor Milica Papko-Hrvojević, and our Vice Dean, Professor Nataša Krejić. And as a beginning of the conference, I would ask Professor Milica Papko-Hrvojević to welcome all of us. Please.
Thank you. Dear participants of the conference, distinguished colleagues, it is my great pleasure to welcome you all on behalf of the Faculty of Sciences and in my personal name, since Professor Takaci I knew for quite a long time. He was my colleague, but I would be free to say also my dear and appreciated friend. I had the honor to get to know him better in 2009 when I was Vice Dean for Science. At that moment, he was the leader of one IPA cross-border project with Hungary. And to my joy, we cooperated often and successfully. And this was not just the honor, but also the opportunity to convince myself in all about his brilliant scientific career. I remember him as a great erudite, real intellectual, and one of this old smithy. He was speaking 4 languages, but he communicated the best in the most universal language in the world, the language of mathematics, which was his occupation and his love. We were really shaken by the fact that we lost one of the most dedicated and most successful mathematicians at the faculty last year, but thanks to Professor Pilipović, Daniela, Nenad, Biljana, Marko, we have opportunity to remember him these days and to give tribute which he deserves. I wish you successful conference and fruitful work in next days. Thank you.
Thank you. Thank you. According to our program, this is opening ceremony, and we will speak about ARPAD. So now, according to our program, we should have a presentation of Professor Kačai from Szeged. I hope that he is here. If he's not, we already prepared his presentation. He has a nice presentation, and as I already discussed with my colleague Jolevska-Tuneska, I would like to ask her to present this presentation. So you will see, we will not speak too much about his life. You will see a lot of pictures. Maybe this is the best way in this moment. I will say something about him later. So, Jolevska, would you like to stay here? Aha, or maybe here, or here, how you like.
In fact, this is the In fact, Professor Kasha told about the cooperation. So this is Professor Kasha talk about collaboration between Szeged University and University of Novi Sad, and these are the picture of Szeged and Novi Sad together. In fact, we introduced Professor Karshai in 2006, where we had started to prepare the first project. Of course, the first application was not so successful, and then the next one was very successful. And these are the pictures of Arpi when he had lecture at Szeged University, and also he has. Okay, no problem. So this is in fact the first our project, the IPA project, and the name was Computer-Aided Modeling and Simulation in Science. This is, in fact, there were two projects in that time. One was from Szeged University, and the other was from the University of Novi Sad, the Faculty of Science, and the name of our part was Development of Computer-Aided Methods in Teaching Mathematics and Science. The next project was in 2010 and 2011. It was together project. It was IPA project, and the name of the project was Teaching Mathematics and Statistics in Science, Modeling and Computer-Aided Approach. And the last project from 2013 to 2015 was non-standard forms of teaching mathematics and physics, experimental and modeling approach. As you can see, each of these three projects was some kind of application of mathematics in science. Sorry. And these are in fact the picture here in Novi Sad at the Faculty of Science. These are team members, as you can see. We have a lot of members, and we have more than 50 colleagues being involved, 2,000 students, 100 teachers, 10 schools, 15 conferences, 20 open day, 4 exhibitions and lectures. And we had really very happy moments. And this is in fact the pictures of our collaboration, of our workshops where we have in Novi Sad and Szeged. In schools in Novi Sad, you can see we have good collaboration and good conferences. That was school in Szeged, school in Novi Sad, 2011, 2011 school in Szeged, 2015, that was one of the last hour conferences, school in Novi Sad, and some other nice pictures. conference moments. This is, I think, Rivers Foster going on this side, this last picture, and the other I will recognize. This is me, Daniela, Steve. I don't know where are these pictures.
Where it is, and it's
I don't know.
river, I don't know.
I don't know. Maybe it was in Austria or something like that.
Ah, yes, it seems.
Something like that, I don't know. Events, open days, we have a lot of together meetings. We've been in Subotica, Saint, Asymptotic, got interdisciplinary crisis. Boyan, and Boyan is here again helping. Training. And these are nice pictures prepared by Saget University. Yeah, and also. We have a lot of collections of teaching material, and we use this during this corona crisis, so it helped. It continues to help. I think this is, the start and second in restaurants.
This is photos.
Our fortress, drinking beer.
Oh, there are many beer.
Oh, sorry.
Thank you, Judith. I should say that actually Judith didn't see this presentation, and I can imagine that this was not so easy for her to present these slides. Very nice presentation of Professor Karczewski. So you will see also Professor Kamiński and Svetlana Kaminska. They will also have a lot of pictures. And I will not have any one of them just because of that. There are so many. But let me say something about Arpad Takacs. I had a lot of talks about him when he died, and so I will not repeat all the facts which I know about him. He was my friend, very close friend. Actually, we started together. I mean, he's younger than me 1 year, but the whole procedure, our education went in the same way. He graduated 1 year after me at the Faculty of Sciences here in Novi Sad, and then master thesis he did in Belgrade, and doctoral thesis again in Novi Sad, as me. So even we did the same field at that time. Of course, Professor Bogoljub Stanković was guided him and myself. So somehow maybe people forgot it. Even I forgot. We started with joint papers. We did something which is now, let me say, popular, pretty popular more than that in that time, with convolutors. If I say Fourier multipliers, then my students will recognize what does it mean. So we started with several papers, and actually he went to Kiev and spent, I don't know, it's half of a year or something like that, half of a year in Kiev with Olaf von Gruzinski, who was actually, Woka was a great professor, very nice person, and Olaf von Gruzinski, who, let me say, who gave that name tempered alpha distributions. Later I call them ultra-tempered alpha distributions. But so this is the history. After him, I also went to Kiev for 3 months. Somehow similar. We went several times to Poland. What I remember from that time, maybe interesting, I didn't speak about that. The biggest conference, generalized functions, this is the name of the conference, was organized by Russians in Moscow. And then we met Sobolev, we met Sato, we met, of course, there were Vladimiro, Mikushinsky, all these friends of us, collaborators of Professor Stankovic. So somehow the Komatsu, so many, Lelong, I cannot remember all the names. So this was really a great experience for us to be on that conference in 1980. Even I have a picture of only one. At that time, we didn't make so many pictures. We were somehow not interested in pictures at that time. So later, Takachi went to another direction. Let me say something also, which is not known. He was the first one who started to study Colombo generalized functions before me. He went to Bordeaux and spent 1 month with Colombo, who is founder together with Oberguggenberger of the whole theory. So somehow later he went to Leicester and cooperate with Brian Fisher. Then Titsa and Arpad spent 2 years in Richmond with Schmelk. And so somehow he has a very strong social communication with mathematicians over the world. Even I think he met also Lavoie when we started with them, and asked me if he will talk about these asymptotic things. Lavoie, who was blind old man and did some work in that field. And somehow on this conference we will have lectures actually which belong to the fields in which Arpad Takachi was involved. So you can see he was really great mathematician, more than 70 papers, 20 in journals, international journals, more than 10 books. So somehow, but maybe he was a director of our department at the time, Institute of Mathematics, I think. Somehow a lot of duties he had, but what was the main point? Main point, he had a nice personality. He was really a man who everybody liked. I could not remember anybody who was somehow in quarrel with Arpad. This was impossible. And so this was really nice. And maybe I can speak, of course, a lot about Arpad. I will just finish with this. He was a nobleman. He was really a nobleman. And this conference I'm happy that we organized this conference. So I will stop in this moment with my presentation of introductory presentation of devoted to Arpad Takachi. And I would like to ask Andrzej Kamiński, I see him, Svetlana, they will say some words about Arpad, and this will end this introductory part of our conference. Please, Andrzej, do you hear me, Andrzej? Svetlana? Now we hear. Svetlana.
Okay.
Yes.
I want to keep our screen. Did you see our screen?
Svetlana?
No.
Andrzej said he's with Svetlana.
Connect by me.
Oni się zapomnieli.
Stavi Sandra, jesi povezati
Evo, sad je Svetlana.
Now Svetlana. No, now.
Okay. I'll try. Leave you.
Sad je na Andrzeju.
Oni zaczynają stąd.
Co sam jest opet zmienił?
Okay. Because they...
Svetlana?
You connect with the computer, Andrzej. Please connect with my computer because there are problems.
Now the Andrei is presenter.
Oh.
Pa ja imam moje imena, ja sam to stavio malo pre da je Svetlana Kaminska presenter.
Please connect with the computer of Svetlana because there.
Svetlana presenter. Ne, Svetlana. A ne, ovdje nemojte da gledate, tamo one je ekranija njihova. Onda treba da share. Svetlana, could you please share your screen?
I'll try.
Možda ću Andreja mutovati, jer...
Okay.
Can I start?
Yes.
Hello, everybody. I would like to present common memories with my wife about the late Professor Arpad Takacsy. Let me start from myself because I knew longer Arpad, almost 40 years. My first visit to Novi Sad was in February 1980. I was then a member of Professor Mikusiński's team in Katowice, and I knew already Professor Bogoljub Stankovic and several of his pupils, but not Arpad Takacsy, whom I met just then. I was captivated by scientific and life dynamics and by great hospitality of all my hosts, but a very special impression on me was made by Arpad. His English was brilliant. His intelligent and general knowledge was imposing. He was a charming and a very warm person. There were then many other common meetings, mainly in Serbia and Poland, and we just invite everybody to look of some pictures from a few of these meetings. This picture is very well known because it is presented in the Institute of Mathematics of Novi Sad. Let me show you some of pictures. This in your seminar room. This is during the excursion to Hruška Gora, 1996. Again, picture together with Professor Filipovic during the conference in 2004 in Novi Sad. Professor Carmichael was Professor Takacs and Professor Carmichael. Professor Bogolyub-Stankovic, together with Professor Arpad Takacs. The Takacs, together with Professor Colombo. It was a very nice visit at the Takacs' home. Takacs and Professor Dymowski, Professor Kiriakova. This is a Georgian mathematician, Terzian. Bulgarian mathematician, Terzian. Okay. Did this conference in Poland at Bendlewo in 2007. It was quite a big conference. Many people, very well known mathematicians are here. Many of them, unfortunately, not alive now. For instance, Krystyna Skórnik died 2 years ago. Professor Antosik died 5 years ago. Professor Bojarski died also. This is the lecture of Professor Takacs. And now he is a chairman, and my wife is talking. There is the talk of son of Professor Jan Mikusiński, Piotr, during the chairmanship of Arpad. This is a very nice picture.
Professor Wysik.
Wysik, Mirjana Stoyanowicz also died already. This is a very nice picture because it was after the conference, and to our team of organizers of the conference, it was so nice that Arpad joined this team. The excursion to Poznań, the famous cathedral in Poznań. Professor Komatsu, Professor Gramchev. Arpad Takacs and Stefan Pilipovich. Unfortunately, one of mathematicians hidden here. This is already
2012.
Fruszka Gora, during another
2012.
Yes, 2000 conference. Also 2012, and Professor Marti, Mirjana, Arpad, my wife. As usual, very nice meeting. Professor Pilipovich, Georgica, Arpad, myself. This is, it should be said that we often were driving from Rzeszów to Gabrovo, Bulgaria, and we stopped just in Novi Sad, and it was a good occasion to see our friends. We often met Arpad and Georgica. This is one of the meeting during this in 2012. Also,
All the family.
the whole family during in 2012 meeting. again, nice picture with the family of Arpad.
Grandson.
This is in Sofia during the conference of 2013.
Complex analysis and applications. Together with Jason Windas
here, Professor Nemtsev from United States. To connected with Professor Iliev, academician Iliev, in Sofia. By night. It is the beauty of Novi Sad by night. Dr. Marty.
Thank you,
Novi Sad,
Andrzej.
2012, the conference in Novi Sad. 18, sorry, 2018. Nice picture.
Nice, very nice. Thank you, Andrzej. Thank you.
Okay.
Mature.
Let us. Okay. This is the last our meeting in August last year. We traveled from Bulgaria. Okay, thank you very much.
Thank you, Andrzej. It was a nice memory to our colleague Arpad. Thank you very much. Now we turn to our main program, the conference. We are late a little. I hope you can understand that not everything can be fixed in this situation. And let me thank to our dean and vice dean. So goodbye. So children or grandchildren also goes. And so I will now announce first the lecture of Elena Teofanov. Elena Teofanov also prepared lecture related to the work of Professor Takaci. His title is Asymptotic Analysis and Distribution, some historical remarks. Please, Professor Teofanov.
Nie ma.
Okay, so we already heard some excerpts from biography of Professor Takaci, whose study stay in Kiel, then PhD thesis in the beginning of the 80s, then study stay in London, Lancaster, Bordeaux. Then he became the director of our institute. And then the thing which I would like to speak about is the so-called blue book on asymptotic behavior and still his transformation of distributions. So this is the main topic of my talk. Then he became director of the Institute of Mathematics again and visited Fulbright. As a Fulbright scholar, visited Virginia University of Richmond, USA. So somehow I met Professor Takaci when I finished my when I graduated, when I finished my undergraduate studies, and then I started the master studies in 1992 for 4 years. And that period saw scientific interest of Professor Takachi in the 80s are reflected in a dozen of papers which are collected in this book, which is survey on many definitions of asymptotic behavior of distributions, their comparison, new results, and application to different problems. So for mathematical review, I will just quote that this book is a remarkable synthesis of the results of the last two decades concerning asymptotic behavior of distributions and their applications to Stieltjes and Fourier transform partial differential equations and abelian type theorems. So, as Professor Filipovic said, that theory somehow became more and more interesting in the 21st century, and it eventually became his most cited reference. So let me say, what is it about this asymptotic analysis of distributions? So we begin with a Littlewood's generalization of the Taubert theorem, and that result, which was published 109 years ago, is by John Benedetto. It is called the first deep Tauberian theorem. The importance of that paper is well explained in several books. For example, there is a book about 12 landmarks of 20th century analysis. So it's really an important result also from this historical point of view. So Taubert theorems are kind of opposed of the converse of the abelian theorems. And the abelian theorem is any statement to the effect that some method of summability gives to each convergent series its ordinary sum. And Tauberian theorem is kind of converse. There is another growth condition to obtain this converse. In other words, summability, well, it means it can also give a summation of divergent series. So this is why we have quotations. Summability plus some another condition, which is commonly called Tauberian conditions, it gives summability by other methods. So let me give just example, well-known. This is the direct theorem, abelian theorem, which says actually that if a series is convergent, then the power series when x tends to 1 give the same, well, from below, give the same limit. But the converse, of course, is false in general because we have a geometric series which converges as 1/2, but when x is 1, we have a divergent series. 1 minus 1 plus 1 minus 1. Okay. So there is an integral analog, which is important of a abelian result. You have, instead of summation, you have integrals, and for example, this is a kind of Laplace transform that you can put the limit inside of the integral sign. Okay. So although this series is divergent, as we saw, we may say that it is other summable to the sum 1/2, because there is another summability method. Any summability method should at least be linear and also regular, which means that to convergent series it gives the same limit. And then Taubert proved that if the n times a sub n tends to 0, so that these numbers are satisfy this condition, this is additional condition, then we have the converse. Okay. So somehow Hardy conjectured that the boundedness of this sequence is enough, should be enough. And then Littlewood actually proved the Hardy conjecture, and in the history of mathematics this is important because that paper started the cooperation. They were in Cambridge and Oxford, and then afterwards they cooperated until the end of the death of Hardy, so more than 20 years, and it is considered as the most productive scientific cooperation in mathematics. So, apart from Littlewood, the next milestone in this theory was Wiener's Tauberian theorem, which is based on the Fourier transform, and it led to new concepts. This is important. So, actually, Wiener introduced generalized harmonic analysis, and actually his theory can be used to prove the prime number theorem, and then it started the work of Gelfand, inspired Gelfand to start the work on what is nowadays called abstract harmonic analysis. So let me give you a Wiener covariant theorem. So for integrable, absolutely integrable function, if its Fourier transform is non-vanishing, and if we have a bounded function, then if the convolution of those two gives the term r times the integral of this absolutely integrable function, then for any other function we have the same conclusion. So here covariant condition, this is additional condition, is boundedness of phi, like boundedness of that sequence, and then G represents this one summability method. And then the conclusion that we have summability for the whole class of functions. So we test it to one function, and then we come to the conclusion that it holds for any other, let me say, summability method. And this is covariant in disguise, covariant condition in disguise. So what Benedetto says in his preface to the famous series of books, Applied Numerical Harmonic Analysis, that the Wiener covariant theorem provides the proper notion of the spectrum for phenomena such as white light. So somehow we have this abstract mathematical theory, but then it gives you a kind of proper understanding of what are some phenomena in physics. What is important for us at this moment is that and then in 1930s, Jovan Karamata, who lived in Belgrade, he is a pupil of Mikhailo Petrovich. So at that time, the country was called Yugoslavia. He gave a surprisingly simple proof of Hardy-Littlewood's theorem, because Littlewood's proof is more than 20 pages, just the proof of one theorem. And Karamata's proof was in 2 pages. And I give another quotation that after Hardy-Littlewood and Wiener, the principal actor was Karamata in this covariant theory. His heritage involving regular variation, we will see what is it, it became indispensable in asymptotic of all kinds. This is from the book Tauberian Theorem, published 15 years ago. So regular invariant function play a role in many parts of mathematics. So you can see at the slide those parts of mathematics. And what is a regular invariant function? We start with a slow invariant function. This is the condition. So it's a function, if you multiply the variable by a, and if this limit is 1 for every number a, then it's called slow invariant. Okay, at infinity. And then if you multiply slow invariant function with power, which is a real number, then you get this regularly varying at infinity. There is a characterization of regular invariant functions. So, instead of infinity, we can consider these functions at origin or at some finite point, and then it is fact that slow and regular variation are preserved under summation and integration. So it turns out that for a large class of functions, you can somehow put this slowly varying function in front of the integral. So, just to conclude this part, Karamata proved abelian and covariant theorems involving regular derivation for Laplace and Stieltjes transform. And this is important because Laplace transform can be defined by the means of fractional integration and fractional derivatives. It depends on this power alpha, which can be positive and negative. So this is all well explained in the blue book. So the topic of this conference about fractional integration is linked to this asymptotic analysis by the Laplace transform. And in 1954, Professor Stankovic defended his thesis under the supervision of Jovan Karamata. And then, as we heard, Stevan Filipovic was one of the pupils of Professor Stankovic, and then some years afterwards, Professor Takachi as well. So we already see this picture of two pupils who started their scientific career at about the same time as the beginning of 80s. So it turned out that slowly varying functions are the natural choice for comparison of function in the asymptotic analysis of generalized functions. So we are now turning, instead of common functions, we are taking another point of view to see how it can enter in the theory of generalized functions or distributions. And this was justified in this great work of Stankovic, Pilipovic, and Takaci. So somehow the asymptotic behavior of distribution was somehow proposed by different people in different notions. And then one of the notions which appear to be very important is the notion of quasi-asymptotic, which was introduced in the context of quantum mechanics. So this was somehow proper notion from asymptotics. Another approach is related to the so-called moment expansions in the work of Estrada, Campbell, and Estrada's pupil, Winters. So quasi-asymptotic, what is important that this kind of asymptotic behavior can be characterized by Tauberian theorems for the Laplace transform. But there is another asymptotic. So quasi-asymptotic is somehow linked to the temporal distributions, but as asymptotic behavior, another kind of asymptotic behavior is somehow convenient if you want to have exponential growth of distributions. So if you want to go beyond temporal distributions, you should use another notion. So somehow the full comparison of those different types of asymptotic is given in what I call the white book. So it's a kind of continuation of the blue book from Pilipovic, Stankovic, and Takaci. Now we have Winters instead of Takaci in this white variant. And I will conclude what happened next. So at the end of the 20th century, Professor Takaci, so when I started my master studies, the wavelet theory somehow started to grow, so it was beginning of the 80s, and then we somehow applied asymptotic given quasi-asymptotics for abelian and Tauberian theorems connected to the wavelet expansions. And then this work influenced later work by Rakic's here, Winters and Pilipovic. They gave a complete study of quasi-asymptotic in that context of the wavelet analysis. So this is done via abelian and Tauberian times. But what is important that I will conclude with this is that actually asymptotic of generalized functions can recover results on usual functions. For example, the Littlewood theorem can be and is given as a just example in the work of Pilipovic, Rakic, and Winters. So somehow they could prove by using generalized functions, they could prove the classical result for ordinary functions. So this is somehow important to stress out. Okay, this is what I would say, that this enlightens the use of theory of distributions in investigations of local properties of functions as well. I will just finish with this slide of Professor Takaci, and thank you for your attention. Thank you, Chairman.
Thank you, Leon. We didn't loud after that. Thank you for this introduction of the whole theory. Maybe I should add something. Now we have a new guy who do these things, Lenny May, who made doctoral thesis 2 months ago in Ghent. He's brilliant guy, and he did now quasi-asymptotics and asymptotics in the frame of alpha distributions with really nice results. So let me, before I continue, just to tell to all our colleagues who are looking at us from the platform that they can send their question by chat. And then I will see these questions, and then I will ask speaker, and he can answer a question. So I continue with the program if there is no other question. Now we have Professor Biljana Jolevska-Tuneska. Let me say that Biljana was his doctoral student, so she's from Skopje. She will present us her talk, but she was very important, and this cooperation with her was for Takacs Arpa very, very important and very nice cooperation. So, Biljana, you hear us?
Yes, yes. Hi, everybody. Thank you very much on the organizers for giving me this opportunity to be a part of this conference dedicated to the memory of Professor Arpad Takacs. I've met Professor Takacs 20 years ago. First in 1999, I was in Blagoevgrad in Bulgaria on a conference where I met Professor Brian Fisher from Leicester University. And he offered me some collaboration then. So he wanted me to go to Leicester to have my PhD degree, but Leicester was very far from me in that time, and I asked Professor Fisher if he knew anyone else that worked in the same area with affiliation closer to Skopje, let's say. And he said, yes, I know one professor and many professors actually from Novi Sad University, but I will recommend you to meet Professor Arpad Takacs and to work on your PhD thesis with him. So I came in Novi Sad and met Professor Takacs. We started our collaboration. 3 years after that, in 2003, I finished my PhD education. But our collaboration didn't finish with me finishing my education in Novi Sad, at Novi Sad University, but we worked with Professor Takacs for 20 years from then, not only when I was his PhD student. We continued our collaboration many years after that. I can say that he was very, very kind man, and that was my first impression of him. And till now, I think that I was very lucky to have him as my PhD advisor. And also, I'm very sorry that he died too young for me. And but that's life, and we have to go on. For today's presentation at the conference organized dedicated to his memory, I have made some points with the fractional calculus, and that is what my presentation is going to be about. I'm going to share now the file. Probably you can see it now all. So I will say a few words about fractional calculus from its origins till now, since this conference is about fractional calculus, which is very popular these days. Fractional calculus is a generalization of the ordinary differential and integration where we put an arbitrary non-integer order. This subject is old as differential calculus, and it goes back to the time when Leibniz and Newton invented differential calculus. So the most common notations for beta order derivative of a function are given here, but we have beta when a positive integer a differential, when a negative values when we have a negative values of beta, that corresponds to fractional integrals. So what we can count as the date for the birthday of the fractional calculus. So I refer to a letter from L'Hopital in 1695, where Leibniz raised the following question. Can the meaning of derivative with integer order be generalized to derivative with non-integer orders? So L'Hopital was somehow curious about this question and asked what if the order is 1/2? And in the letter dated, as we know, September 30th, 1695, Leibniz answered that it will lead to a paradox, from which one day useful consequences will be drawn. So we consider this date to be the birthday of the fractional calculus. After that, many mathematicians contributed to this theory over the years: Louisville, Riemann, Weil, Fourier, Grunwald, Letnikov, and others. So these days we have lots of studies, especially in application of mathematics, where lots of new things are included, and our fractional calculus is used to have better modeling of some problems. Next, where we can start. We have a derivative. The question is, does we have any operator H called half derivative such this following equation holds? We can generalize this question and have a operator P on the power of alpha that the next relation holds. And for all this, we need the gamma functions. So the gamma function is very tight with the fractional calculus by its definition. Also, we can, let's say, have some operator J with these properties. And this, if we have a double integral, we have a J square operator. All of this can be extended to J on the power of n. So given by this repeated integration formula of Cauchy. Also, we can now use the gamma function to remove the discrete nature of the fractional function and have some other form of the same integral, fractional form of the same integral operator. So basically, Euler in 1730 used this formula with the gamma function. Then Fourier, a little bit later, by means of integral representation, give the following definition. Abel used also integral representation for arbitrary alpha. After that, Louisville, in his first definition, generalized the formula using the exponential representation of the function. And after that, he gave the second type of his definition as a fractional integral. Also later on, he worked a lot on these topics, and we have his third definition, which includes fractional derivative. the definition of Riemann of fractional integral is given with this relation, and after that in Sorin, Letnikov, and Laurent work with Cauchy integral formula to obtain another definition of fractional operator. So we have let's say today we work with 3 types of definitions for the fractional operator. That is Riemann-Liouville definition, Grudwald-Letnikov definition, and Caputo's definition. So today they are the main tool for working fractional calculus. Here I borrow one picture from Professor Virginia Kiryakova's work about how the history of fractional calculus went. And we have in the beginning Newton and Leibniz, famous mathematicians from 3 centuries ago, and lots of other mathematicians during the years, including in the work of the fractional calculus. Today, not only mathematicians, today other people, especially I would say electroengineers working in the topics of fractional calculus, and using the developed tool to get more precise models, more precise models. So next, I gave some actually derivatives, fractional derivatives for some function. Here on this picture are the fractional derivatives for the identity function, for the constant function. And here we have fractional derivatives for identity function. The fractional derivatives of some order, negative and positive, for the exponential function. Also, the fractional derivative for the sine function. And we can see for this picture that why this topic has a very big exploitation in electrotechnical sciences, let's say, because all the fractional derivatives are with the same similar shape, let's say, for the sine function also, and for the cosine function, very, very similar. So also here I tried to make some list of where I could find application of the fractional calculus, and the list was very long. I couldn't make the end of it, since starting with numerical methods, then advancements of calculus of variation and optimal control to fractional dynamical systems, some application in materials, then fundamental exploration of the mechanical, electrical, and thermal constitutive relation and other properties of various engineering materials, fractional differentiation for edge detection, image and signal processing, thermal modeling of engineering systems such as brakes and machine tools, fractional control of engineering systems. This is very popular today because they get better and better results in this area. Also, at the end, bioengineering and biomedical application of the fractional calculus, etc. So many application of the fractional calculus, and a lot of people, not mathematicians, every day is getting a new idea how to make the fractional calculus applicable to their fields of research and their fields of interests. So thank you very much for your attention. If you have any questions, I think.
Sorry, yes, it's on. If you have some question or remark, if not, thank you very much, Vidana.
Thank you again.
We will continue our program. Actually, we are on time, even some minutes. We have 7 minutes, so we can continue in 7 minutes. Let me say that next two speakers are Professors Michael Oberguggenberger and Hans Feichtinger, and so probably they hear us. They are, and I see them, not yet. So let's wait a little, and then we will continue in 5 minutes. We will continue. Please, here we have coffee, we have many things, even we have some